Hello there, and welcome to The Sleepy Scholar. Tonight's journey takes us out into the vastness of the quiet, breathing world of trees. We will wander together through ancient forests, beneath whispering canopies, and down into the patient, hidden networks that thrive within the soil, exploring the silent majesty of these essential guardians of our world. There is a profound peace to be found in the presence of trees. They are the Earth's eldest storytellers, standing witnesses to the slow procession of centuries, their roots anchored in history and their branches reaching for the infinite. They ask nothing of us but to be, to breathe alongside them, to feel the gentle filter of sunlight as it finds its way through their leaves, and to remember the deep, slow rhythm of life that beats just beneath the surface of our awareness. If you enjoy these quiet explorations, consider subscribing so you can easily return here whenever you need to rest. But for now, get comfortable. Let your eyes grow heavy. Let's begin. One of the oldest known living individual trees is a Great Basin bristlecone pine named Methuselah, located in the White Mountains of California, estimated to be over 4,850 years old. This ancient being first pushed its way through the harsh rocky soil when human civilization was only just beginning to write its earliest stories, long before the Great Pyramids of Egypt rose from the desert sands. It lives in a place of extremes, a high-altitude desert where thin air, scarce water, and relentless winds would deter almost any other form of life. Yet it is this very adversity that has granted it such profound longevity. The tree grows with a patience we can barely comprehend, its wood becoming incredibly dense and resinous, a natural fortress against decay, insects, and the erosion of time itself. For nearly 5 millennia, it has stood in quiet contemplation, a silent observer of the turning stars and the slow shifting of the mountains. Its gnarled, twisted form, a beautiful sculpture, carved not by an artist, but by the slow, persistent breath of survival, reminding us that resilience often finds its deepest roots in the most challenging of landscapes. There is a vast, hidden network beneath the forest floor, often called the Wood Wide Web, where trees communicate and share resources through an intricate web of mycorrhizal fungi. This subterranean society is a place of quiet cooperation, a sprawling, delicate lace of fungal threads that connect root to root, tree to tree, creating something that behaves less like a crowd of individuals and more like a unified forest community. Through these fungal bridges, older, more established mother trees can send vital nutrients like carbon and nitrogen to younger seedlings struggling for sunlight in the deep shade, nurturing the next generation. It is not just nourishment that flows through this network. Trees can also send chemical warning signals, alerting their neighbors to insect attacks or disease, allowing them to raise their own defenses before the threat arrives. This silent, interconnected web helps transform the forest from a place of simple competition into a complex, interdependent neighborhood, a testament to the profound hidden alliances that sustain life in the shadows of the earth. The tallest living trees on earth are the coast redwoods, Sequoias sempervirens, with the reigning monarch, named Hyperion, soaring to a height of nearly 380 feet. To stand at the base of such a giant is to feel a sense of profound awe, craning your neck to see a crown that seems to touch the very heavens, a living pillar that bridges the gap between the soil and the sky. These titans thrive in a very specific, narrow band of coastline in California and Oregon, where they drink deeply from the persistent coastal fog, absorbing moisture directly through their needles in the dry, summer months. Their existence is a marvel of natural engineering. An intricate system of capillaries must defy gravity to pull water hundreds of feet upward from the earth, sustaining leaves that photosynthesize in a realm far removed from the forest floor. They are ancient cathedrals of the natural world, their massive, fire-resistant trunks chronicling centuries of history, inviting us to consider the sheer scale and persistence of life. Trees release airborne chemicals called phytoncides to protect themselves from insects and disease, and inhaling these compounds has been shown to significantly benefit human health. When you walk through a pine forest and breathe in that sharp, clean, resinous scent, you are inhaling these protective molecules, a form of ancient airborne medicine gifted by the trees. These invisible compounds are the tree's immune system, its silent guardians against the threats of the forest. For humans, the simple act of breathing this forest air, a practice known in Japan as Shinrin-yoku, or forest bathing, can have remarkable effects. Studies have shown that these phytoncides can increase the activity of our own natural killer cells, a vital part of our immune defense, while simultaneously reducing the production of stress hormones, calming the mind, and lowering blood pressure. A gentle reminder that our own well-being is inextricably linked to the health of the natural world. Some trees, like aspens, reproduce through a process called vegetative cloning, creating massive underground root systems that send up genetically identical shoots, forming a single colossal organism. The Pando colony in Utah is a stunning example. A single quaking aspen organism covering over 100 acres, comprised of thousands of individual-looking trees that all share one massive root system. This entire forest, weighing an estimated 13 million pounds, is, in essence, one single tree, potentially making it the heaviest and one of the oldest living organisms on Earth, with estimates of its age reaching back thousands, perhaps even tens of thousands of years. Each trunk is a temporary expression of this ancient, underlying life force, living and dying in cycles while the organism itself endures, a vast unified consciousness sleeping beneath the soil, demonstrating a form of immortality where the whole persists long after the individual parts have returned to the earth. The unique, swirling patterns found in burwood are the result of a tree healing itself from stress, injury, or infection, creating a dense, chaotic, and beautiful growth pattern. A burl is essentially a tree's scar tissue, formed when its normal growth patterns are disrupted by fungi, bacteria, or physical damage, causing the cells to divide and grow in a wild, unpredictable, and condensed manner. Instead of growing in straight, uniform lines, the wood grain twists and eddies around these points of trauma, creating intricate, map-like figures that are prized for their unique beauty. What we see as a flaw or an imperfection is actually a record of the tree's resilience, a physical manifestation of its ability to contain a wound, to compartmentalize damage, and to continue growing around it. These gnarled, beautiful forms are a testament to the idea that immense strength and complex beauty can arise directly from places of hardship and healing. A single mature oak tree can be a vibrant ecosystem unto itself, providing food and shelter for hundreds of different species of insects, birds, fungi, and mammals. From its deep roots to its highest leaves, every part of the oak is a source of life. Its acorns are a crucial, energy-rich food source for countless animals, from squirrels and deer to jays and turkeys, fueling them through the harshness of winter. The rough, deeply fissured bark provides a haven for insects and spiders, which in turn become food for birds like nuthatches and creepers that meticulously explore every crevice. Its broad canopy offers nesting sites and protective cover from predators and the elements, while its leaves feed a multitude of caterpillar species, forming the foundational layer of a complex food web. Even after an oak has lived its long life, its decaying wood continues to give, becoming a home for fungi, beetles, and microbes that recycle its nutrients back into the soil, ensuring that its legacy of generosity continues. The baobab trees of Africa, Madagascar, and Australia have evolved to store massive quantities of water in their thick, fibrous trunks, allowing them to survive long, intense periods of drought. These magnificent trees, often appearing as if they were planted upside down with their root-like branches stretching to the sky, are masters of endurance, living reservoirs in arid lands. During the brief rainy season, a large baobab can absorb and store thousands of gallons of water, swelling its trunk noticeably as it prepares for the dry months ahead. This stored moisture not only sustains the tree, but also provides a vital lifeline for elephants and other animals, who will often chew on the soft, fire-resistant bark to access the water within. The baobab is a central figure in many local cultures, revered as a tree of life, a place of gathering, a source of traditional medicine, and a powerful symbol of community and resilience in landscapes where water is the most precious gift of all. Dendrochronology is the science of dating past events by studying the annual growth rings of trees, providing an incredibly detailed living record of history. Each year, a tree adds a new layer of growth just beneath its bark. This ring is wide in years of favorable conditions, with ample rain and sun, and narrow in years of drought, cold, or hardship. This simple, repeating pattern forms a precise calendar, a biography of the tree's life, written in wood. By cross-referencing the patterns of living trees with those of ancient wood found in archaeological sites or preserved in bogs, scientists can build continuous chronologies stretching back thousands of years. These wooden archives tell us far more than just age. They reveal past climates, pinpoint the dates of volcanic eruptions, help date ancient settlements, and even show us the timing of distant cosmic events whose energetic particles subtly altered the chemistry of the rings, allowing these silent wooden witnesses to speak of the Earth's and even the cosmos's past. Some trees have evolved to be fire-dependent, meaning their life cycles are intricately linked with, and even require, the presence of periodic wildfires for their seeds to germinate. The lodgepole pine, for example, produces serotinous cones, which are sealed shut with a strong, hard resin that protects the seeds inside. These cones will remain closed, sometimes for decades, clinging stubbornly to the branches, even as the tree grows around them, waiting patiently for a specific cue. That cue is the intense, searing heat of a forest fire, a force that most life flees from. The fire's heat melts the resin, allowing the cone to finally open and release its cache of seeds onto a newly cleared forest floor, now enriched with ash and free from the competition of shady undergrowth. This remarkable adaptation transforms a moment of apparent destruction into the very catalyst for new life, ensuring that the forest will be reborn from the embers, a perfect cycle of renewal orchestrated by the trees themselves. The ginkgo biloba is often referred to as a living fossil because it is the last surviving species of a division of plants, Ginkgo phyta, that has existed for over 270 million years. This tree is a true relic, a survivor from a time when dinosaurs walked the earth. Its unique fan-shaped leaves, almost identical to fossils left behind in ancient rock. It has outlasted countless other species, enduring ice ages, continental shifts, and mass extinction events with a quiet, unshakable persistence. Its resilience is legendary. Ginkgo trees are incredibly resistant to pests, diseases, and urban pollution, which is why they are often planted in bustling cityscapes. Most astonishingly, 6 ginkgo trees located near the epicenter of the atomic bombing in Hiroshima, Japan, though badly charred, survived the blast and quickly budded new leaves, standing as powerful, living symbols of endurance and the unyielding tenacity of life in the face of utter devastation. The phenomenon of crown shyness is an observed behavior where the topmost canopies of certain tree species avoid touching each other, forming a beautiful maze-like pattern of channels in the sky. When you stand beneath a grove of these trees, such as camphor or eucalyptus, and look directly up, you will see a stunning natural mosaic, as if each tree has politely agreed to respect its neighbor's personal space. The exact reason for this behavior is still a gentle mystery debated among scientists. Some believe it is a way to prevent the spread of leaf-eating insects from one crown to the next. Others suggest it is a response to the physical abrasion of branches rubbing together in the wind, which damages the delicate growing tips. It may also be a sophisticated strategy to optimize light exposure for all leaves, ensuring that no single tree completely overshadows its neighbors, creating a cooperative and beautiful architecture of light and space. Trees are vital carbon sinks, meaning they absorb more carbon dioxide from the atmosphere than they release, playing a critical role in regulating the Earth's climate. Through the quiet, sun-powered miracle of photosynthesis, a tree breathes in the carbon dioxide that we exhale and that our industries produce, and it transforms that gas into life itself. It splits the molecules, releasing the oxygen we need to breathe and locking the carbon away within its own body, building it into its leaves, its branches, its trunk, and its roots. A forest is a vast living vault of stored carbon, captured and held safely in solid form, keeping it from warming the atmosphere. The older and larger a tree becomes, the more carbon it can hold, making ancient forests invaluable allies in the quest for balance, tirelessly working to clean our air and buffer our planet against climatic change. The Bodhi tree, a sacred fig located in Bodh Gaya, India, is revered by Buddhists as the very tree under which Siddhartha Gautama, the Buddha, attained enlightenment. This specific tree, or more accurately its direct descendant, is a profound spiritual landmark, a living connection to a pivotal moment in human consciousness. The original tree, which lived for many centuries, became a destination for pilgrims who would come to sit in its shade, seeking the same peace and insight that was discovered there. Cuttings from it have been planted around the world, most famously the Jaya Sri Maha Bodhi in Sri Lanka, which was propagated in the 3rd century BCE and is itself the oldest known human planted tree, with a continuous historical record. The tree itself, with its distinctive heart-shaped leaves, represents the sheltering canopy of wisdom, a place of stillness and profound realization, its roots anchored in the earth while its spirit touches the transcendent. Mangrove trees possess a remarkable ability to thrive in saltwater environments, a feat that would be lethal to almost any other tree. thanks to a sophisticated set of filtration and salt exclusion adaptations. These resilient trees stand at the boundary of land and sea, their tangled, stilt-like roots plunging directly into the salty tidal waters. Some mangrove species have roots that act as ultra-efficient filters, blocking the salt from ever entering the tree's vascular system. Other species tolerate the salt's entry, but then actively excrete the excess through special glands in their leaves, leaving visible salt crystals behind as the water evaporates. Their complex root systems also trap sediment, gradually building up the land, and act as a vital submerged nursery for countless species of fish and crustaceans, all while forming a living, breathing seawall that protects coastlines from the erosive power of storm surges and waves. Many trees enter a state of dormancy during winter, a deep and necessary sleep that allows them to conserve energy and survive the cold, dark months. This is not a passive process, but an active, internally regulated shutdown, triggered by the shortening days and cooling temperatures of autumn. The tree begins by meticulously reabsorbing the valuable nutrients, like chlorophyll, from its leaves, which is why they turn those brilliant shades of yellow, orange, and red before they fall. With its leaves gone, the tree seals off the connection points, minimizing water loss. Its metabolism slows to a crawl, its pulse becoming almost imperceptible as it ceases to grow and focuses all its energy on simply surviving, living off the stored sugars it created during the sunny summer months. It rests, patiently waiting in the frozen soil, holding the promise of spring deep within its buds, a perfect model of restorative stillness. The angel oak tree in South Carolina is a southern live oak estimated to be several hundred years old, famous not for its height, but for the magnificent, sprawling expanse of its branches. This ancient matriarch covers an astonishing 17,000 square feet of ground, with its shade, its massive limbs not reaching upward, but sweeping outward and downward, many resting gently on the earth for support before turning back up to the sky. To stand beneath its canopy is to be inside a living room sculpted by nature, a vast, shaded sanctuary where branches twist and turn like the arms of a gentle giant. Its presence feels less like a single tree and more like a small, tranquil forest in itself, a testament to the power of growth that moves not just toward the sun, but also in connection with the ground that supports it, a symbol of enduring, sheltering grace. The sap of a tree is actually two different fluids moving through two different networks: xylem, which carries water up from the roots, and phloem, which transports sugars from the leaves. The xylem is like a bundle of microscopic straws, pulling water and dissolved minerals on a one-way journey from the deepest root tips all the way to the highest leaves, a process driven by the evaporation of water from the leaf surfaces, known as transpiration. The phloem, conversely, is the tree's circulatory system for food, a pressurized network that carries the energy-rich sugars produced during photosynthesis down to feed the trunk, the branches, and the roots, or to be stored for later use. This intricate dual plumbing system works silently and constantly, a perfect, balanced flow of nourishment and hydration that allows the tree to drink from the earth and eat from the sky. The strangler fig begins its life not in the soil, but as a seed deposited by a bird or mammal high in the canopy of a host tree. From this lofty perch, the fig seedling sprouts, sending its roots down the trunk of the host, slowly, patiently making its way to the forest floor. As its roots find purchase in the earth, the fig's growth accelerates dramatically. It sends more roots downward, and branches upward, creating a dense, woody lattice that envelops the host tree's trunk entirely. Over many decades, the fig's embrace tightens, its own canopy growing thick and broad, stealing the sunlight from its host. The fig's roots outcompete the hosts for water and nutrients in the soil. Eventually, the original host tree, starved of light and resources, and constricted by the fig's woody cage, dies and rots away, leaving the magnificent hollow trunk of the strangler fig standing alone, a beautiful and ruthless monument to the slow, inevitable cycles of competition and succession in the forest. The bristlecone pines have a unique survival strategy, where parts of the tree can die off in order to sustain the whole, allowing it to live for millennia in harsh conditions. In their high-altitude homes, where soil is thin and nutrients are scarce, these trees cannot afford to support a full, lush crown. Instead, as the tree ages, large sections of its bark and the living tissue beneath it will slowly die back, channeling all of the tree's limited resources into just a few living branches and a narrow strip of bark. This strip of life, often just a few inches wide on a trunk that is many feet in girth, is all that is needed to connect the living leaves to the few roots that can find water. This process creates the gnarled skeletal appearance they are famous for, with vast regions of dead, golden wood polished by wind and time, standing next to a single, vibrant, living branch, a perfect emblem of extreme efficiency and persistence. The ancient yew tree is known for its remarkable longevity, capable of living for thousands of years, and for the profound toxicity found in almost every part of its being. This tree is a guardian of paradox, often found standing sentinel in quiet churchyards, its deep green foliage a symbol of everlasting life, while its needles, bark, and seeds hold a potent, deadly secret. This toxicity is not a mark of malice, but a sophisticated, evolved defense, a chemical armor that has protected it from browsing animals and decay for millennia, allowing it to achieve its great age. The wood itself is incredibly strong yet flexible, prized by ancient bowyers, but it is the tree's relationship with time that is most awe-inspiring. Ancient yews often become hollow, their heartwood decaying away while the outer layers of sapwood continue to live, and they can even send down new roots from their branches or trunk interior, regenerating themselves from within. They are living ruins, existing in a slow, patient cycle of decay and rebirth that transcends our own understanding of a single lifetime. Trees play a fundamental role in the planet's water cycle, acting as enormous biological pumps that draw moisture from the soil and release it into the atmosphere through a process called transpiration. A single large oak tree can lift hundreds of gallons of water from the earth each day, pulling it up through its xylem network and releasing it as invisible vapor from tiny pores, or stomata, on the undersides of its leaves. This collective breath of a forest is a powerful force, a gentle, silent river flowing upward into the sky. This released moisture contributes significantly to local humidity and cloud formation, meaning that forests actively help to create their own rain. This beautiful, self-sustaining loop, where the trees cool down the very water they need to survive, demonstrates a profound and intricate connection between the living world and the atmosphere, a partnership that shapes regional climates and sustains the very greenness of the earth. The rainbow eucalyptus, native to the Philippines, Indonesia, and Papua New Guinea, is a tree that appears to be painted by an artist. Its trunk, shedding bark in patches, to reveal a spectrum of vibrant colors. Unlike other trees, its exfoliation is not a uniform event, but a continuous staggered process where strips of its outer bark fall away at different times throughout the year. When a piece of bark first peels off, it reveals a bright, electric green layer of inner bark. As this new layer is exposed to the air, it begins its slow transformation, darkening and maturing through a palette of blues, purples, and oranges, before finally settling into a deep reddish brown just before it, too, is shed. This constant, evolving patchwork means the tree's trunk is a living canvas, never a single solid color, but a perpetually shifting mosaic of vertical stripes, a breathtaking and whimsical display of nature's hidden vibrancy. Petrified wood is a type of fossil that forms when a tree's organic material is replaced by minerals over millions of years, turning the wood into solid stone. This remarkable transformation begins when a tree dies and is quickly buried by sediment or volcanic ash, protecting it from the decay that would normally be caused by oxygen and microbes. Over vast stretches of geologic time, water rich in dissolved minerals, such as silica, slowly seeps through this buried wood. This mineral-laden water flows through the tree's cells, and as the original woody material, the lignin and cellulose, slowly breaks down, the minerals are left behind, crystallizing in their place. This process is so precise that it often preserves the tree's microscopic structure, including the delicate cell walls and the distinct patterns of the growth rings, creating a perfect heavy stone replica of the original organism, a beautiful and enduring record of an ancient forest written in crystal. The General Sherman tree, a giant sequoia in California's Sequoia National Park, holds the title of the largest tree in the world by volume, a colossal monument of life. It is not the tallest nor the widest at its base, but the sheer, staggering immensity of its trunk contains more wood than any other tree on Earth, weighing an estimated 2.7 million pounds. To stand near it is to feel humbled by a living being that has persisted for well over 2,000 years, a quiet contemporary to the rise and fall of empires, its massive, reddish-brown trunk soaring nearly 300 feet into the sky. This tree continues to grow, adding new wood each year, a volume equivalent to an entirely new, mature tree. It is a slow-motion explosion of life, a testament to the monumental potential stored within a single seed, its enormous, fire-scarred presence, a quiet reminder of endurance, scale, and the profound, patient power of the natural world. Trees can communicate with each other by releasing volatile organic compounds, or VOCs, which are essentially airborne chemical messages that warn neighboring trees of danger. When a tree is attacked by insects, such as a caterpillar chewing on its leaves, it doesn't just suffer in silence. It actively releases a specific blend of these chemical signals into the air, a fragrant plume of alarm that drifts through the forest. Nearby trees, even those of different species, can intercept and interpret this message. Upon receiving the warning, the neighboring trees, though untouched themselves, will begin to ramp up their own defenses, such as producing bitter-tasting tannins or other toxins in their leaves to make them less palatable to the approaching insects. This invisible chemical conversation is a beautiful example of a community's shared awareness, a network of silent, fragrant warnings that help the entire forest protect itself through collective intelligence. The bark of the willow tree has been used for millennia as a source of medicine, as it contains a compound called salicin, which is the natural precursor to the active ingredient in aspirin. Ancient civilizations, from the Egyptians to the Greeks, recognized the willow's gentle power, prescribing its bark and leaves to soothe fevers and ease pain. They would chew the bark or brew it into a tea, finding relief from the plant's innate chemical wisdom. This natural compound works by calming the body's inflammatory response, a gift from a tree that often grows in damp, marshy places. The discovery and isolation of salicin in the 19th century directly led to the synthesis of acetylsalicylic acid, or aspirin, one of the most widely used medicines in the modern world, a powerful reminder that the sophisticated chemistry of our pharmacies often has its deepest roots in the quiet, healing knowledge held within the plant kingdom. The plants we commonly call palm trees are not, botanically speaking, true trees at all, as they belong to a group of flowering plants known as monocots, which also includes grasses and lilies. Unlike true trees or dicots, like oaks and maples, palms do not have traditional woody tissue. They do not produce bark in the same way, and they do not form growth rings that widen their trunks each year. Instead, their trunks are composed of fibrous, vascular bundles, much like a bundle of straws bound tightly together, which is why their trunks remain relatively uniform in diameter as they grow upwards. Their growth originates from a single large bud at the very top of the plant, the heart of palm. If this central bud is damaged, the palm cannot regenerate and will cease to live. This fundamentally different architecture makes them a unique and ancient lineage of plants that have simply adopted a tree-like form to reach for the sun. A beautiful example of nature arriving at a similar solution through a completely different evolutionary path. The manchineal tree, found in the tropical regions of the Americas, is known as one of the most potent and guarded trees in the world, with every part of it containing a complex array of powerful toxins. This tree is not malicious, but rather a master of self-preservation, having evolved an incredibly effective chemical defense system to protect itself from being eaten. Its milky, white sap is famously caustic, and even standing beneath its branches during a rain shower can be unwise, as the water dripping from its leaves can carry these compounds. The small, apple-like fruit it produces is equally deceptive, a powerful warning to all who might consume it. Local peoples have long respected this tree's boundaries, often marking it with a red X to warn others. The manchineel is a profound example of nature's chemical ingenuity, a living fortress that commands respect and illustrates the powerful unseen forces that plants can wield in their silent, rooted lives. When a tree is wounded, whether by a storm, an animal, or a pruning saw, it does not heal the injury in the way an animal does. Instead, it seals the damage off through a process called compartmentalization. This defense system, known by the acronym CODIT, or compartmentalization of decay in trees, is a masterful strategy of containment. The tree immediately establishes 4 distinct barrier walls around the wound. The first wall slows the vertical and inward spread of decay, while a third wall slows the radial spread. But the fourth and most powerful wall is a new layer of strong protective wood that the tree begins to grow around the site of the injury. This new growth does not repair the damaged tissue, but instead seals it off forever, like a ship sealing a breached compartment to save the rest of the vessel. This is why you can often see old wounds or hollows in trees that are otherwise perfectly healthy, a visible scar from the past that has been successfully walled off, allowing the tree to continue its life, growing forward around its history. The tule tree, an ancient Montezuma cypress located in Oaxaca, Mexico, is famous for having the widest, most massive tree trunk in the entire world. This colossal being, known locally as El Árbol del Tule, has a trunk circumference of nearly 140 feet, a staggering girth that is so broad it is difficult to perceive as a single tree. It is not a collection of fused trunks, as was once believed, but one single unified genetic individual that has been growing for an estimated 1,500 to 3,000 years. Its massive, gnarled base resembles a merging of great stone pillars, creating nooks and buttresses large enough to seem like architecture. The tree's crown is a vast, sprawling canopy that casts an immense, life-giving shade, creating a gathering place for the entire community. It stands as a living testament to sheer volume and endurance, a quiet, breathing mountain of wood that has become the heart and soul of the town that grew around it. Banyan trees, which are a type of fig, possess an extraordinary growth habit, sending down aerial roots from their branches that grow into thick, woody trunks, allowing a single tree to spread into what appears to be a dense grove. This process often begins when a single banyan grows a long, horizontal branch. From this branch, thin, dangling roots emerge, reaching downward through the air, sometimes for great distances until they touch the soil. Once they anchor themselves, these roots thicken, becoming indistinguishable from the main trunk, acting as new pillars to support the ever-expanding canopy. This allows the banyan to grow outwards indefinitely, creating a magnificent, sprawling labyrinth of interconnected trunks and branches. The great banyan tree in India, for example, covers several acres and appears to be a large forest. Yet it is all one single ancient organism, a living cathedral with countless columns, each one a new expression of the tree's relentless drive to expand and support its massive, sheltering presence. Trees are nature's own gentle air conditioners, creating vital microclimates that significantly cool the surrounding environment. They achieve this cooling effect through two primary methods. The first is the simple, welcome gift of shade. Their dense canopies act as living umbrellas, blocking the sun's harsh direct radiation and preventing the ground and air beneath them from absorbing that heat. The second, more complex method is evapotranspiration, the same process by which they release water vapor from their leaves. This process is, in essence, tree sweating. Just as perspiration cools our skin as it evaporates, the water vapor released by leaves draws energy in the form of heat from the surrounding air, actively lowering the ambient temperature. A single large tree can have a cooling effect equivalent to several room-sized air conditioners running for a day, providing a quiet, selfless, and life-sustaining service that makes our cities and wildlands more habitable. The dragon's blood tree, found on the remote island of Socotra off the coast of Yemen, is a plant of otherworldly appearance, with a dense, upturned, umbrella-shaped canopy that looks sculpted by the wind. Its most remarkable feature, however, is the deep crimson-red resin it produces, which gives the tree its evocative name. When the bark is cut or injured, this dark red sap slowly bleeds out and hardens, a substance that has been sought after since antiquity. This dragon's blood was not just a curiosity, it was a highly prized commodity, used as a potent medicine, a vibrant pigment for paint and dye, and even as a varnish for violins. The tree's strange mushroom-like shape is a brilliant adaptation to its arid environment, its tightly packed leaves channeling the precious moisture from coastal mist down its branches and trunk to its roots, a marvel of natural engineering that allows it to thrive where little else can. The quiver tree, or cocoa-boom, is not a true tree, but a species of aloe that grows to tree-like proportions in the arid landscapes of southern Africa. It has earned its name from the San people, who traditionally hollowed out its light, fibrous, and tubular branches to create quivers for their hunting arrows. This plant is a master of desert survival, its thick, succulent leaves storing precious water, and its smooth, whitish bark covered in a fine powder that reflects the intense sunlight, helping to keep the plant cool. The bark itself is patterned with sharp-edged scales, giving it a prehistoric reptilian appearance. Its branches fork and refork, creating a dense, rounded crown that bursts with bright yellow flowers in the winter, providing a rare and vital source of nectar for birds and insects in the harsh, dry season, a true beacon of life in the desert. The division between deciduous and evergreen trees represents two fundamentally different, yet equally successful strategies for surviving the challenges of the changing seasons. Deciduous trees, like maples and oaks, are the opportunists, investing their energy in creating wide, thin, highly efficient leaves that capture vast amounts of sunlight during the warm, bright growing season. But these leaves are tender and vulnerable to freezing. So as winter approaches, the tree wisely cuts its losses, reabsorbing the leaves' nutrients and shedding them, entering a deep dormancy to conserve water and endure the cold. Evergreens, like pines and firs, are the conservatives. They invest heavily in creating tough, waxy, needle-like leaves that are more resistant to cold and water loss. While less efficient at photosynthesis at any given moment, these durable leaves can persist for several years, allowing the tree to photosynthesize on any mild or sunny day, even in the depths of winter, ensuring a slow, steady, and patient persistence. Trees are the silent, patient architects of the soil, and its most steadfast guardians. Their life's work begins as their roots delve into the earth, breaking apart compacted soil and even solid rock, creating pathways for air and water to penetrate deep underground. When their leaves, branches, and eventually their entire bodies fall and decay, they infuse the soil with a rich, dark layer of organic matter called humus, building the very fertility that sustains future generations of life. Simultaneously, their vast, intricate root systems act as a living net, a fibrous web that clasps the soil and holds it in place. This tenacious grip prevents the precious topsoil from being washed away by rain or blown away by wind, protecting our landscapes from the ravages of erosion and ensuring that the land remains stable, fertile, and alive. The roots of a tree are far more intelligent and sensitive than they appear, possessing a remarkable ability to sense their immediate environment and navigate it with purpose. The very tip of each growing rootlet, a tiny structure called the root cap, is a marvel of perception, able to detect gravity, water gradients, and the chemical signatures of nutrients. But perhaps most impressively, it can sense physical obstacles. When a root tip encounters a rock or a compacted, impenetrable layer of soil, it doesn't just push forward aimlessly. It will actively grow along the path of least resistance, feeling its way around the barrier to find a clearer passage. This gentle, persistent exploration, this thigmotropism, or response to touch, is a slow-motion dance of navigation, ensuring the tree can build a vast, efficient network to anchor itself and find the resources it needs, all conducted in the patient silence of the earth. The acacia trees of the African savanna have formed a profound symbiotic alliance with certain species of stinging ants, a partnership that benefits both organisms immensely. The tree provides its tiny guardians with a complete, custom-built home, offering hollow thorns called domatia that serve as safe, fortified barracks for the ant colony. The acacia also provides for all their nutritional needs, secreting a sweet nectar from special glands on its leaves and producing protein-rich nodules at the tips of its leaflets, called Belgian bodies. In exchange for this room and board, the ants serve as a vigilant 24-hour security force. They swarm aggressively at the slightest disturbance, fiercely attacking any large herbivore, like a giraffe or elephant, that tries to browse on the acacia's leaves, biting and stinging the animal's sensitive mouth and trunk. They also protect the tree by clearing away any encroaching vines or competing seedlings that sprout at its base, ensuring their host tree remains safe, healthy, and dominant in the landscape. The ancient art of bonsai is a profound, meditative practice that explores the relationship between humanity and nature, using horticultural techniques to cultivate miniature trees in containers that mimic the form and scale of their full-sized counterparts in the wild. This is not the creation of a new dwarf species. Rather, it is a long, patient dialogue with a normal tree, gently guiding its growth over many decades, sometimes centuries, through careful pruning of both branches and roots, and by wiring its branches to shape their direction. The goal is not to force the tree into an unnatural form, but to express its essential character and the beauty of its struggle against the elements, evoking the image of an ancient windswept pine on a mountainside or a graceful maple by a riverbank. It is a living art form that requires deep understanding, patience, and a respect for the tree's own life force. A quiet collaboration that captures the majesty of time and nature in a small, contemplative form. The concept of a mother tree is a central part of the wood wide web, referring to the largest, most established trees in a forest that act as vital hubs, nurturing the surrounding community. These ancient matriarchs, with their vast root systems and expansive canopies, are often the most deeply connected individuals in the fungal network, linking them to hundreds of other trees, both young and old. Through this subterranean web, they appear to support the forest much like a wise elder. They can send excess carbon, which they gather through their abundant, sun-drenched leaves, down through the fungal pathways to feed shaded, understory seedlings that are struggling for light, giving them the energy they need to survive their vulnerable youth. Some experiments suggest that these elders may even favor their own kin, sending a little more nourishment to their direct offspring than to unrelated neighbors. Though this subtle kin recognition remains an area of active study. When a mother tree is aging or dying, it can release a final, generous pulse of nutrients and carbon into the network, a last gift that helps sustain the next generation. A beautiful, selfless act that strengthens the resilience of the entire forest community. The unique bark of the paper birch tree, which peels away in thin, papery, horizontal layers, is a brilliant adaptation to its environment and has been invaluable to human cultures. This smooth, white bark is imbued with a waxy, oil-based compound called betulin, which makes it remarkably waterproof, durable, and resistant to decay, even when the wood inside has rotted away. The tree sheds its outer layers as it expands, a gentle exfoliation that also helps it cast off mosses, lichens, and potential pests. For the indigenous peoples of North America, this bark was a profound gift from the forest. They could carefully harvest it in large, flexible sheets, without causing permanent harm to the tree's living inner cambium layer. This pliable, resilient, and waterproof material was then skillfully stitched together to create the lightweight, swift, and legendary birch bark canoe, as well as to craft containers, baskets, and the coverings for their dwellings, a perfect and respectful partnership between human ingenuity and the tree's natural generosity. The Osage orange tree produces a large, heavy, and bumpy green fruit that is almost entirely inedible to native wildlife, a puzzling evolutionary mystery known as an evolutionary anachronism. This strange softball-sized fruit, with its citrus-like scent and bitter, milky sap, simply falls to the ground and rots, as no existing North American animal has the digestive system to process it or the inclination to eat it. Scientists believe this fruit is a ghost from a bygone era, a relic from the Pleistocene, when the continent was home to massive megafauna like giant ground sloths, mammoths, and mastodons. It is theorized that these enormous animals, now extinct for over 10,000 years, were the tree's intended seed dispersal partners, the only creatures large enough to consume the hefty fruit whole and pass the seeds unharmed. The tree continues to faithfully produce its obsolete fruit, a living memory of a lost world, still waiting for the giant gardeners who will never return. The sap of the maple tree, which is boiled down to create maple syrup, is a very specific fluid that flows only during the unique freeze-thaw cycle of early spring. This is not the tree's sugary phloem from the summer, but rather a special pressurized flow within its xylem, the water-conducting tissue. During the cold nights, the tree's woody fibers freeze, and the gases within them contract, creating a vacuum that pulls water up from the roots into the trunk. Then, as the daytime sun warms the tree, the ice thaws and the trapped gases expand, creating a positive pressure, around 20 pounds per square inch, that forces the slightly sweet, watery sap to flow out of any wound or tap hole. This sap, which is over 98% water, contains sugars that the tree stored in its roots all winter, now being moved upward to fuel the budding of new leaves. It is a brief, magical window of time, a hydraulic pulse driven by the changing of the seasons that gives us its fleeting liquid gold. Trees that grow in extremely windy, coastal, or alpine environments often develop a stunted, asymmetrical shape known as Krummholz, which is German for crooked wood. This is not a genetic trait, but a physical record of the tree's long, persistent struggle against the relentless force of the wind. On the windward side, the constant icy and abrasive gales, often carrying salt or ice particles, effectively prune the tree, killing off new buds and drying out the branches, preventing any growth in that direction. In response, the tree channels all its life force into the branches. On its leeward side, the sheltered face protected by its own trunk. This results in a dramatic flag-like appearance, with all the foliage streaming away in one direction, or in the most extreme locations, a dense matted carpet of branches that crawls along the ground. A beautiful and poignant sculpture carved by the invisible, powerful hand of the wind. The phenomenon of ramial wood refers to the small diameter branches and twigs of a tree, which have been discovered to be the most nutrient-dense and biologically active part of the entire organism. While we often focus on the massive trunk or the leafy canopy, it is these youngest branches, typically less than 3 inches in diameter, that contain the vast majority of the tree's easily accessible minerals, proteins, and sugars, as they are the active growing tips of the tree. When these branches are chipped and return to the earth as mulch. They decompose in a unique way, fostering an explosion of beneficial fungi rather than just bacteria. This fungal-dominant compost is precisely what forest soils need, rebuilding the rich, spongy, and resilient soil structure that trees thrive in. A perfect, closed-loop system where the tree's own prunings become the ideal food for its roots and the foundation of a healthier forest. The pau-brasil, or Brazilwood tree, is so central to the history of its nation that it gave the country its name, and in doing so, nearly vanished from the earth. This tropical tree, which grows in the Atlantic forest, was prized by Europeans who arrived in the 16th century for one specific hidden treasure, its heartwood. When cut, the wood reveals a deep fiery red interior that, when ground and boiled, produced an exceptionally potent and valuable red dye, a color that was rare and highly sought after in the Old World, for coloring luxurious textiles. This discovery ignited a massive, centuries-long logging rush as the Terra do Brasil, or Land of Embers, was stripped of its namesake trees. The Brazilwood, which had simply been living quietly, became the economic engine of a colony, its beautiful blood-red heart, a symbol of both immense value and devastating exploitation, a living piece of history that is now the focus of intense conservation efforts to bring it back from the brink. The olive tree is a profound symbol of peace, resilience, and longevity, capable of surviving for millennia in poor, rocky, and arid soils where few other fruit trees could endure. Its tenacity comes from its remarkable root system, which can spread wide and deep, patiently seeking out moisture, and its unique ability to regenerate even when its main trunk is damaged or appears dead. If the above-ground tree is cut down or burned, new shoots or suckers will often emerge from the surviving root crown, allowing the tree to be reborn from its own base. Its leaves are also perfectly adapted, with a silvery green, waxy coating that reflects the harsh sun and minimizes water loss. This ability to bear fruit year after year, century after century, in the challenging Mediterranean landscape, made it a sacred, life-sustaining gift to ancient peoples. Its oil a source of food, light, and medicine, and its branch a timeless emblem of reconciliation and enduring life. The Joshua tree, a species of yucca, is a striking and iconic plant of the Mojave Desert, defined by its bizarre, fuzzy, and angular branches that reach out in all directions like the arms of a storybook giant. It relies entirely on a single, tiny, nocturnal partner for its survival, the yucca moth. This relationship is a masterpiece of coevolution, a pact of mutual exclusive dependence. The female moth emerges at night and flies to the creamy white bell-shaped flowers of the Joshua tree. She deliberately collects pollen from one flower, forming it into a sticky ball, and then flies to another flower. There, she performs an incredible act. She carefully climbs down the flower's pistil and lays her eggs inside the flower's ovary, and then, in the same motion, she purposefully smears the pollen ball onto the stigma, ensuring the flower is pollinated. This act guarantees that the flower will produce seeds, which will serve as the only food source for her developing larvae, who eat only a small portion, leaving the rest to create the next generation of trees. Each organism is the sole key to the other's future, a perfect fragile lock of interdependence in the quiet of the desert night. The giant redwoods of California have bark that is a marvel of natural engineering, a thick, fibrous, and spongy armor that can be up to 2 feet thick, providing incredible protection from one of their greatest natural threats, fire. This rust-colored bark is surprisingly lightweight and soft, but it is profoundly fire-resistant. It contains very little flammable resin or pitch, and its thick, porous structure acts as a powerful heat shield, insulating the living cambium layer beneath from the searing heat of forest fires. This protective cloak allows the mature trees to stand, often unscorched, while smaller, competing trees are cleared away by the flames. Furthermore, the bark and heartwood are incredibly rich in tannins, chemicals that make the tree highly resistant to decay and insect infestation. This combination of defenses is why these giants can live for thousands of years. Their massive trunks a living fortress, patiently enduring the trials of time. The Japanese practice of daisugi is a centuries-old, sustainable forestry technique that involves pruning a mother cedar tree in such a way that it produces numerous, perfectly straight, and slender trunks that grow vertically from its base, like a natural living lumber plantation. This ingenious method, which originated in the 14th century, allowed foresters to harvest high-quality uniform timber without ever cutting down the main tree, thus preserving the ancient parent and the forest floor. The shoots are carefully cultivated for years, pruned meticulously so they grow knot-free, and then harvested in a rotating cycle, while the mother tree itself can live for hundreds of years, continually producing new generations of timber. It is a profound, living example of human ingenuity, working in perfect harmony with a tree's natural growth patterns, a system of patience and foresight that treats the forest not as a resource to be consumed, but as a garden to be tended. The banyan tree and the sacred fig are known as keystone species in their tropical forest ecosystems, meaning their presence is critical to the survival of a vast number of other species. Their importance stems from their unique, asynchronous fruiting cycle. Unlike most trees that fruit seasonally all at once, individual fig trees produce their fleshy, inverted flowers, or figs, at staggered, seemingly random times throughout the year. This provides a reliable, year-round, walk-in pantry for a huge array of animals, especially fruit-eating birds, bats, and monkeys. During the lean months when other food sources are scarce, the figs from a single, fruiting banyan can become the sole lifeline for the forest's frugivores, sustaining the entire community. This central, nourishing role makes the fig tree a living cornerstone, a focal point of activity and survival around which the complex web of forest life is woven. The poplar tree is one of the fastest growing temperate trees in the world, a sprinter in the slow marathon of the forest world, often used in reforestation projects because it can establish a canopy and stabilize soil with remarkable speed. This rapid growth is fueled by a high-efficiency photosynthetic system and a voracious appetite for water, its roots driving quickly and aggressively toward moisture. But this speed comes with a trade-off. Its wood is light, soft, and relatively weak compared to its slow-growing counterparts like the oak. Poplars live their lives in a rush, reaching for the sun, serving their ecological purpose quickly, and often having a much shorter lifespan. They are the pioneers, the first responders after a disturbance. Their soft, pale wood, a testament to a life spent prioritizing speed. A gentle reminder that in nature, there are many different, equally valid, strategies for success. The color of a tree's leaves is determined by pigments, and the brilliant autumn transition is not an act of creation, but one of revelation. Throughout the spring and summer, the leaves are dominated by chlorophyll, the powerful green pigment that captures sunlight for photosynthesis. This green is so abundant that it masks all other colors present in the leaf. As autumn approaches, the shortening days and cooler temperatures signal the tree to prepare for winter dormancy. It stops producing new chlorophyll and begins to break down the existing green pigment, reabsorbing its valuable nitrogen components back into the trunk for storage. As this dominant green fades away, it unmasks the other pigments that were present in the leaf all along, the vibrant yellows and oranges, known as carotenoids. The deep reds and purples, or anthocyanins, are a separate, final flourish produced by some trees in the autumn sun from trapped sugars, a beautiful, fiery goodbye before the leaf finally lets go. The Kari trees of New Zealand are ancient forest giants, belonging to a lineage that stretches back to the Jurassic period, and they are renowned for the high-quality golden-hued gum, or copal, that bleeds from their bark. This resin, which hardens into a glassy amber-like substance, was a treasure, prized by the Maori for generations as a fire starter and for tattooing, and later harvested extensively by European settlers for use in fine varnishes. These trees have a unique self-pruning habit, shedding their lower branches as they grow, resulting in a massive, clean, columnar trunk that soars upward before unfurling a majestic crown. Most remarkably, these trees live in deeply interconnected communities. Scientists have discovered that the root systems of living Kari trees can graft together with the stumps of long-felled trees, keeping them alive for decades, nourishing their ancient leafless neighbors in the dark. A profound and mysterious example of collective memory and support within the forest. The cherry tree, celebrated around the world for its breathtaking, ephemeral spring blossoms, holds a deep cultural significance, particularly in Japan, where it is known as sakura. The beauty of the cherry blossom is prized not just for its delicate pale pink and white clouds of flowers, but for the very fact that it is so fleeting, often lasting for only a week or two before the petals are scattered by the wind. This brief, spectacular display is seen as a profound metaphor for the nature of life itself, a moment of intense, perfect beauty, followed by the inevitability of its passing. This concept, known as mono-no-aware, or the gentle, bittersweet awareness of transience, is a cornerstone of Japanese aesthetics. The annual hanami, or flower viewing parties, are a time of celebration, but also a quiet, collective meditation on renewal, hope, and the beautiful, temporary nature of our own existence. The ancient cedars of Lebanon, Cedrus libani, are among the most famous and historically significant trees in the world, majestic conifers whose endurance and high-quality timber shape civilizations. These trees, mentioned in the Bible and the Epic of Gilgamesh, grow slowly in the harsh, high-altitude mountains of the Near East. Their wood is incredibly durable, aromatic, and resistant to insects and rot, a combination of qualities that made it the most prized building material of the ancient world. It was this wood that was used to construct Solomon's temple in Jerusalem, the palaces of kings, and the great sea-going ships of the Phoenicians. These trees were so valuable that they were logged almost to extinction, their vast ancient forests reduced to a few precious protected groves. To stand in one of these remaining groves is to be in the presence of living antiquity, a silent witness to the very foundations of human history. The bark of the cork oak tree, native to the Mediterranean, has a unique, regenerative property that allows it to be harvested without killing the tree, a practice that has sustained ecosystems and economies for centuries. The tree's outer bark is an exceptionally thick, lightweight, and spongy layer of dead cells, an evolutionary adaptation to protect it from the region's frequent fires and arid climate. This cork layer is a natural insulator, buoyant and impermeable to water. Every 9 to 12 years, skilled harvesters can carefully peel this outer bark from the trunk in large sheets, a process that, when done correctly, leaves the tree's living inner bark, or phloem, completely unharmed. The tree then begins the slow, patient work of regenerating a new cork layer, a process it can repeat for over 200 years. This gentle, sustainable harvest creates a unique forest landscape, the Montado, an open woodland that is a hotspot of biodiversity, a perfect model of a harmonious, long-term relationship between people and trees. The phenomenon of masting is a synchronized survival strategy where all the trees of a single species in a large area, such as oaks or beeches, will produce a massive, overwhelming glut of seeds in the same year, followed by several years of very little seed production at all. This is not a response to immediate weather conditions, but a deep, collective, and internally regulated rhythm. The strategy is twofold. In the lean years, seed-eating predators like squirrels, mice, and birds are kept to a low, stable population, as there is not enough food to support a boom. Then, in the mast year, the trees suddenly and collectively produce far more seeds than this small population of predators could ever possibly consume. This predator satiation ensures that while many seeds are eaten, a vast number are left untouched, guaranteeing that a significant number will survive to germinate and become the next generation of the forest, a brilliant, synchronized tactic of feast and famine. The mysterious crooked forests found in places like Poland and Russia, where stands of pine trees grow with a uniform 90-degree bend at their base, are a curious puzzle of nature. In these groves, every tree, after growing straight for a few inches from the ground, makes a sharp, J-shaped curve to grow horizontally for several feet before turning back upward to the sky, creating an eerie and beautiful collection of natural sculptures. The cause of this uniform curvature has been lost to time, though many theories exist. Some believe it was a deliberate human intervention, that the young saplings were intentionally bent and shaped, perhaps to cultivate compass timber for boat building or furniture making, though no historical record confirms this. Others propose a natural cause, such as a catastrophic snowstorm or blizzard that pinned the young, flexible saplings down for a prolonged period, forcing them all to grow in this direction before they could correct their course to the sun, leaving behind a silent, graceful monument to a long-forgotten event. The heartwood of a tree is, botanically speaking, entirely dead. Yet it is this very non-living core that provides the tree with its greatest structural strength and durability. This dense, inner column of the trunk is formed as the tree ages, when the older inner layers of xylem, or sapwood, cease to transport water and become filled with protective chemical compounds. The tree actively infuses this dying wood with resins, tannins, and dark-colored gums, a process that makes the heartwood incredibly hard and resistant to the invasion of fungi and insects. This transformation is a wise internal sacrifice, where the tree lets go of the life in its center in order to build a powerful, unyielding spine. This solid, preserved core is what allows the tree to soar to great heights, to withstand the force of powerful winds, and to endure for centuries, a silent, internal monument to the idea that great strength can be found in the parts of us that have already lived, transformed, and settled into a profound, supportive stillness. The thin, living layer of cells just beneath the bark, known as the cambium, is the true engine of a tree's growth, a place of constant, quiet creation. This delicate, almost invisible tissue, often only a few cells thick, is a ring of undifferentiated stem cells, holding the tree's entire potential for expansion. It is a place of perpetual division. When a cambium cell divides, it creates two new cells. One cell, on its outer side, becomes a new phloem cell destined to transport sugars, while the other cell, on its inner side, becomes a new xylem cell destined to transport water. This continuous two-way production is what forms the tree's annual growth rings. The xylem is the wood itself, and the phloem is the inner bark. All the massive girth of a giant oak, all its strength and volume, originates from the patient, microscopic, and tireless work of this one single, delicate, living layer, a perfect, hidden factory of life. The phenomenon of phototropism is the innate tendency of a plant to grow toward its light source, a slow motion dance of survival orchestrated by a light-sensitive hormone called auxin. This hormone is produced at the very tip of a growing shoot or branch and is, in a sense, shy of the light. It migrates away from the sun, accumulating in the cells on the shaded side of the stem. In these shaded cells, the auxin acts as a powerful growth accelerant, causing them to elongate and divide much faster than their sunlit counterparts. This differential growth, where one side of the stem grows faster than the other, is what physically causes the shoot to bend and curve, turning its leaves ever so slowly toward the life-giving rays of the sun. This simple, elegant mechanism ensures that the tree can always maximize its access to energy, a silent, internal compass that perpetually guides its growth toward the light. The bristle, or needle, of a coniferous tree is a masterpiece of evolutionary design, a leaf perfectly engineered to endure in environments where water is scarce or locked away as ice. Unlike the broad, soft leaves of deciduous trees, the needle is a compact, hardened structure with a very low surface area, which dramatically reduces the amount of water lost to the dry air or winter winds. This needle is coated in a thick, waxy cuticle, a waterproof seal that locks moisture inside. Even the stomata, the tiny pores through which the tree breathes, are recessed, tucked away in grooves or pits to protect them from the wind's drying grasp. This resilient water-wise design allows the evergreen to continue photosynthesizing, albeit slowly, through the harshest conditions, holding onto its foliage for years, a testament to a life built not on seasonal excess, but on year-round, patient, and unwavering conservation. The mysterious whispering or rustling sound of wind in the trees, often called citharism, is a complex acoustic phenomenon created by the wind's energy being transformed into sound by the leaves and branches. As the air flows over and around these countless, varied obstacles, it breaks its smooth laminar flow and dissolves into thousands of tiny, chaotic vortices and eddies. Each leaf, acting like a small, fluttering flag, creates a tiny pocket of turbulence, and the collective sound of these millions of micro-vibrations, these tiny disturbances in the air, merges into the single, soothing, rushing sound we hear. The specific character of the sound changes with the tree. The fine needles of a pine create a high-pitched, soft shh, while the large, broad leaves of a sycamore create a lower, more percussive, clattering rustle. It is the tree giving a voice to the invisible, turning the silent movement of the air into a gentle, forest-wide exhalation. Some species of trees, like the lodgepole pine and the eucalyptus, have evolved to become pyrophytes or fire lovers, actively encouraging and exploiting fire to ensure their own success. The eucalyptus, for example, is filled with highly flammable aromatic oils, the very substance that gives it its sharp, clean scent. Its bark often peels away in long, dry ribbons that hang from the branches, creating perfect tinder, and its leaf litter is slow to decompose, accumulating on the forest floor as a thick, dry fuel bed. This design ensures that when a fire does arrive, it burns with incredible speed and intensity, a conflagration that clears out all the less fire-adapted competitors. The eucalyptus itself, however, is built to survive this inferno. Its vital buds are protected deep beneath its thick bark, and many species will resprout vigorously from their base, or lignotuber. After the fire has passed, their seeds now free to germinate in a sun-drenched, ash-fertilized, and competition-free landscape. The seeds of many trees possess an incredible inbuilt patience, a state of deep suspended animation known as dormancy, which ensures they only germinate when the conditions are truly right for survival. This dormancy is not simply a passive waiting. It is an active biological lock that must be opened by a specific environmental key. For some seeds, this key is the intense, abrasive process of scarification, needing to be tumbled in a rocky riverbed or pass through the acidic digestive tract of an animal to weaken their tough, protective seed coat. For many others, the key is cold stratification, a requirement to experience a prolonged period of cold, damp winter weather. This cold exposure triggers an internal hormonal clock, a gradual countdown that, once complete, allows the seed to burst into life only after the dangers of frost have passed and the warmth of spring has truly arrived. A perfect, timed release mechanism for the next generation. The practice of coppicing is an ancient symbiotic form of woodland management where trees are intentionally cut down to their stumps, not to kill them, but to stimulate the growth of numerous new, slender, and straight stems from the base. This technique, which has been used by humans for thousands of years, harnesses the tree's natural regenerative response to injury. When the main trunk is removed, the vast established root system, now full of stored energy, pours all its resources into its dormant stool buds, resulting in a rapid explosion of new growth. These new poles, which can be harvested on a sustainable, rotating cycle every 7 to 20 years, provide a constant, renewable source of wood for fencing, firewood, and charcoal, all without ever destroying the forest itself. It is a living partnership, a human-guided dance with the tree's life force that allows the woodland and the stump itself to remain productive and alive for many centuries. The pale, ethereal, and ghostly plant known as the ghost pipe or Indian pipe is not a typical plant. It is a mycoheterotroph, a forest dweller that has completely abandoned photosynthesis and with it all of its green chlorophyll. This waxy white plant, which looks more like a strange fungus, survives by tapping into the hidden subterranean network of the forest. It is, in essence, a thief, but a gentle one. It connects its own roots to the mycorrhizal fungi that are, in turn, connected to the roots of the surrounding trees, typically beeches and pines. The ghost pipe then siphons off the sugars and nutrients that the fungi have received from the trees, a parasite not on the tree itself, but on the fungal bridge between them. It thrives in the darkest, most shaded parts of the forest floor, a pale, silent creature of the deep woods that has found a way to live entirely on the surplus of its green, sun-fed neighbors. The Janka hardness test is the industry standard for measuring the resistance of a species of wood to denting and wear, a process that reveals the immense, hidden density of certain trees. The test itself is beautifully simple. It measures the amount of force, in pounds force, required to embed a small 0.444-inch steel ball halfway into a sample of wood. The results reveal a vast spectrum of strength. On the soft end is balsa wood, a feather-light material that requires only around 100 pounds of force. In the middle are woods like red oak and maple, the dependable standards for furniture. And then, at the far extreme, are the ironwoods of the world, like the lignum vitae, or wood of life. This tropical wood is so dense, so heavy, and so infused with its own waxy resin that it requires over 4,500 pounds of force to mark, a material so tough it was historically used for ship propellers and bearings, a true testament to the quiet, immovable strength that a tree can build within itself. Many trees form protective, symbiotic relationships with bacteria that live within their root systems, most notably the rhizobia bacteria that form nodules on the roots of leguminous trees like acacias and honey locusts. These trees have evolved a sophisticated chemical dialogue with these specific soil microbes. The tree's roots release flavonoids, a signal that invites the rhizobia to approach. In response, the bacteria release their own signal, causing the tree's root hairs to curl and form a small, protected nodule, a custom-built house for the bacteria to live in. Inside this safe haven, the bacteria perform a near-magical feat. They take inert, unusable nitrogen gas from the air trapped in the soil and fix it, converting it into ammonia and other nitrogen compounds that the tree can absorb as a powerful fertilizer. In exchange, the tree provides the bacteria with a steady supply of energy-rich sugars, a perfect, self-sustaining partnership that enriches the tree and the very soil it lives in. The reaction wood a tree creates, known as tension wood in hardwoods and compression wood in conifers, is a remarkable active response to physical stress, allowing a tree to correct its posture and bear immense loads. When a tree is pushed from its vertical path, perhaps by a prevailing wind, a heavy snow, or by growing on a steep slope, it actively senses this lean. A hardwood tree, like an oak, will create tension wood on the upper side of the lean. This specialized wood is built with unique gelatinous fibers that are designed to pull, actively hoisting the branch or trunk back upward against the force of gravity, like a set of internal muscles. A conifer, like a pine, does the opposite. It builds compression wood on the lower side of the lean, creating dense, lignin-heavy cells that are designed to push, propping the trunk up from below. This incredible internal structural engineering allows a tree to remain balanced, to reach for the light, and to bear its own growing weight against the constant pull of the earth. The marcescence of some trees, particularly oaks and beeches, is the curious and beautiful habit of retaining their dead, withered leaves throughout the entire winter, long after all other deciduous trees are bare. These trees go through the normal process of autumn. The chlorophyll fades, the leaves turn a crisp, papery brown, and a separation layer, or abscission zone, forms at the base of the leaf stem. But for some reason, this separation is not completed. The dry, rustling leaves cling stubbornly to the branches, a ghostly bronze rattling in the winter wind. The reason for this is a quiet mystery. Some scientists suggest it may deter large browsing animals like deer from eating the tender, living buds, as the dry, unpalatable leaves get in the way. Others theorize that as these leaves finally fall in early spring, they provide a fresh, timely mulch and nutrient boost for the tree's roots, just as the new growing season begins. The roots of trees are not solitary explorers. They actively encounter and respond to the roots of their neighbors, demonstrating a remarkable to recognize self from other. When a tree's root grows and encounters another root in the dark, crowded soil, it can chemically sense whether that root belongs to itself or to a different tree. If the root is its own, it will often graft, fusing its tissues with the other root to share resources and create a more efficient, interconnected network. However, if the root belongs to a different, unrelated tree, it will often exhibit stranger recognition and actively inhibit growth, steering away to avoid direct competition. But in a forest of related trees, this rule changes, as related kin will often allow their roots to graft, sharing resources and forming the foundation of the cooperative, family-based networks that sustain the forest. A complex, hidden social life based on touch and chemical identity. The hydraulic redistribution performed by trees is a gentle, passive, and profoundly generous act that benefits the entire ecosystem around them. During the night, when the tree is not actively photosynthesizing and its stomata are closed, its deep taproots continue to draw water from the wetter, lower soil layers. But instead of this water traveling all the way up to the leaves, it will often leak or be exuded from the tree's shallower, finer roots into the dry, parched upper layers of the soil. The tree, in essence, becomes a passive fountain, pulling water from the deep earth and sharing it with the surface. This hydraulic lift creates a small, vital oasis of moisture around the tree's base, providing a life-saving drink for the tree's own shallow roots and for all the surrounding understory plants and soil microbes that would otherwise perish in a drought. A quiet, nocturnal act of generosity that stabilizes the entire community. The aileron layer in a seed is a specialized protein-rich skin that acts as a living, intelligent sensor, a gatekeeper that must be activated before the seed can germinate. This layer, which is just inside the seed coat, surrounds the starchy, sugary endosperm, the seed's main food supply. When the seed absorbs water and the proper temperature conditions are met, the embryo wakes up and releases a special plant hormone, gibberellin. This hormone travels to the aileron layer and switches it on, signaling it to begin producing powerful enzymes. These enzymes then flood into the endosperm, breaking down the complex, stored starches and proteins into simple sugars and amino acids. This liquefied, nutritious soup is then fed to the tiny, growing embryo, providing the sudden, massive burst of energy it needs to break free from its shell and push its first root down into the earth, a perfect sequenced internal awakening. The whitebark pine of the high Rocky Mountains has evolved a complete and beautiful dependence on a single bird, the Clark's nutcracker, for its very survival This high-altitude pine produces large, nutritious, wingless seeds that are locked inside a tough, resinous cone that never opens on its own. The nutcracker, with its long, powerful beak, is one of the few birds capable of efficiently prying these cones open and extracting the seeds. But the bird does not eat them all at once. It is a meticulous hoarder, a scatter hoarder, that will collect tens of thousands of these seeds each autumn. It flies them, sometimes for miles, and buries them in thousands of small, hidden caches in the soil as its winter food supply. The bird's spatial memory is astonishing, allowing it to relocate most of its caches, even under deep snow, but it never finds them all. The thousands of forgotten seeds, planted perfectly by the bird in the open, sunny clearings it prefers, become the seedlings of the next generation, making this partnership the primary way the whitebark pine renews itself, its entire future entrusted to the memory and the forgetting of its feathered partner. The Antarctic beached trees, or Nothofagus, found today in South America, Australia, and New Zealand, are a living testament to the slow, relentless, and majestic drift of the continents. These ancient trees, with their distinctive small crinkled leaves, are the direct descendants of forests that once covered the supercontinent of Gondwana, a landmass that connected all of these now distant lands with Antarctica. Fossils of these very trees, millions of years old, have been found on the Antarctic continent, showing that the frozen, icy landscape was once green, temperate, and forested. As Gondwana broke apart, these trees were carried, like silent, passive passengers, on the separating tectonic plates. Their modern distribution is not the result of seeds crossing vast oceans, but rather a living, leafy map of deep geologic time, a fragmented family of trees that still whispers of a single, unified, ancient world. The cotyledon is the first leaf, or pair of leaves, that emerges from a germinating seed, and it functions as the plant's vital first aid kit, or packed lunch, providing all the energy it needs before it can reach the sun. These are not true leaves. They are embryonic leaves, preformed and packed with stored food that were folded tightly within the seed. When the seedling first breaks the soil, it is incredibly vulnerable. Having not yet developed the chlorophyll-rich true leaves, it needs to photosynthesize and make its own food. The cotyledons unfurl and provide that initial critical burst of energy, feeding the seedling's growth as it establishes its roots and pushes its first true leaves up to the light. Once these true leaves have opened and begun to work, the cotyledons, their purpose served, will wither and fall away, their generous preparatory sacrifice having successfully launched the new tree's life. One of the world's most remote, isolated trees is a solitary Sitka spruce on New Zealand's subantarctic Campbell Island, its nearest neighbour over 170 miles away. This tree is not native to the island. It is a profound anomaly, a lonely traveller believed to have been planted by a former governor of New Zealand in the early 1900s. It has not just survived in the harsh, peaty, windswept environment. It has thrived, growing into a large, gnarled specimen. But its isolation is absolute. As the only tree of its kind for hundreds of miles, it lives in a state of reproductive solitude. It produces cones, but with no other spruce to cross-pollinate with, its seeds are infertile. This loneliest tree in the world has become an unexpected and vital scientific tool. Its wood, free from the pollen contamination of other trees, provides a remarkably clean and precise record of changes in the chemistry of the Southern Ocean atmosphere. A silent, solitary sentinel, diligently recording the recent history of our planet's air. The strange, tumor-like growths, known as galls, particularly those found on oak trees, are not diseases, but are in fact intricate, custom-built nurseries created by the tree under the chemical command of an insect. This bizarre and fascinating process begins when a tiny gall wasp, often smaller than a grain of rice, lays its single egg inside the tree's living tissue, such as a leaf bud or a twig. As it deposits the egg, it also injects a unique potent chemical cocktail, a set of instructions that hijack the tree's normal growth mechanisms. The tree, in response to this alien command, abandons its normal cellular development and begins to grow a new specialized structure around the developing larva. This gall is a perfect living fortress. Its outer layers are hard and woody for protection, while its inner layers are rich in starch and nutrients, providing a constant dedicated food supply for the larva. The tree is, in essence, forced to build and provision a safe, personalized cradle for its own parasite, a testament to the profound and almost invisible power of chemical manipulation in the natural world. The incredible strength and rigidity of wood, the very quality that allows a tree to defy gravity and stand hundreds of feet tall, comes from a complex natural polymer called lignin. This substance is a marvel of organic engineering, a dense cross-linking molecule that infiltrates the tree's cellulose cell walls, transforming them from soft, flexible fibers into a hard, composite material, much like adding rebar to concrete. Lignin is the glue of the plant world, binding the cells together and giving the trunk its profound compressive strength and stiffness. This evolutionary innovation was one of the most important steps in the history of life on Earth, as it was lignin that allowed plants to first grow tall, to compete for sunlight, and to form the world's first forests. This substance is also incredibly difficult to break down. It is what causes wood to decay so slowly, a powerful protective matrix that endures long after the tree has fallen, patiently holding its structure and its stored carbon. The annual shedding of leaves by deciduous trees is not a passive, haphazard falling, but a highly controlled, active, and deliberate process called abscission. As the days shorten and the light wanes, the tree prepares for its winter dormancy by initiating a careful, pre-planned separation. At the base of each leaf stalk, a special layer of cells, the abscission layer, begins to form. This layer has two parts. On the side closest to the leaf, the cells are weak and designed to break, while on the side closest to the twig, a protective, corky layer of cells forms, a leaf scar. This scar is a vital, pre-made seal, like a scab, that will protect the tree's open wound from water loss and infection once the leaf is gone. The tree first salvages all the valuable nutrients from the leaf, and only when this process is complete and the seal is ready, does it allow the connection to sever, letting the leaf fall gently to the ground, a perfect, clean, and intentional release. A mature tropical rainforest is a world built in layers, a complex vertical city of life with 4 distinct strata, each with its own unique climate and community of residents. At the very top is the emergent layer, where a few giant solitary trees thrust their crowns far above the rest, living in a harsh world of intense sunlight, high temperatures, and strong winds. Just below them is the canopy, the dense, continuous, leafy ceiling of the forest, a vibrant, green roof where the vast majority of life is found, a world of monkeys, birds, and insects that may never touch the ground. Beneath this thick umbrella lies the understory, a realm of deep filtered shade, high humidity and stillness, home to smaller trees, shrubs, and large leafed plants adapted to life in the dim, greenish light. Finally, there is the forest floor, a dark, quiet, and rapidly recycling world, where the thin soil is quickly fed by the rain of falling leaves and debris, and life is dominated by fungi, insects, and the shadows of the giants above. The bark of a tree is its unique and essential armor, a protective skin that varies in its texture and strategy just as much as the leaves in its canopy. This incredible diversity is a tapestry of evolutionary solutions to the challenges of survival. The smooth, thin, almost muscular-looking bark of a beech or a cherry is a defense against insects and fungi that might try to find a foothold, offering no cracks or crevices to hide in. In contrast, the deeply furrowed, rugged bark of an oak or a pine is a thick, fire-resistant shield, an ablative, insulating layer that protects the living cambium from heat. The shaggy, peeling bark of a hickory or a paperbark maple is a clever form of self-cleaning, a way to shed mosses, lichens, and clinging vines that might otherwise smother the tree. From the waxy, white, sun-reflecting bark of a birch to the corky, fortress-like bark of a sequoia, each texture is a different, perfect answer to the questions posed by its world. The Palo Verde tree, a green stick, that is the state tree of Arizona, is a masterpiece of drought adaptation, a plant that has learned to photosynthesize not just with its leaves, but with its entire body. This desert tree thrives in arid, sun-scorched lands by producing a smooth, waxy, and vibrant green bark, which is rich in chlorophyll. During periods of mild, wet weather, it will produce tiny, delicate leaves, but when the heat and drought become too intense, it quickly sheds these leaves to conserve precious water. This is when its brilliant adaptation takes over. The tree's green trunk and branches assume the full responsibility of photosynthesis, using their vast surface area to continue creating energy from the sun, even when leafless. This allows the tree to remain alive and productive, a beautiful, glowing green sculpture in the desert, having turned its very structure into a living solar panel, a perfect example of life's refusal to surrender to scarcity. When a great tree falls in an old-growth forest, its life's work is far from over. It begins a new, long, and profoundly generous chapter as a nurse log, becoming a cradle for the next generation. As this massive trunk lies on the forest floor, it begins the slow, patient process of decay, its woody tissues becoming a vast, spongy reservoir of moisture and a slowly releasing bank of locked-away nutrients. In the competitive, shaded understory, the forest floor is a difficult place for a tiny seed to sprout, but the surface of this decaying log is a perfect, elevated haven. It lifts the seedling above the damp, crowded floor, offering it a disease-free, nutrient-rich, and water-retentive bed to set its first roots, often giving it just enough of a head start to reach for the light. Walk through an ancient forest, and you will often see a perfect straight line of mature trees, all growing in a row, their roots still straddling the ghost of the fallen giant that nourished their infancy, a beautiful, living testament to the forest's continuous cycle of life, death, and selfless inheritance. The trees known as pioneer species, like the birch, alder, and some pines, are the brave, adventurous first responders of the natural world, the first to colonize land that has been left barren by fire, landslide, or human activity. These hardy trees are not built for long-term dominance, but for speed, resilience, and opportunity. Their seeds are often tiny, lightweight, and equipped with wings or fluff, designed to be carried vast distances by the wind, allowing them to be the first to arrive in a new open space. They are specialists in full sun conditions, growing with incredible speed to stabilize the raw, exposed soil with their roots and quickly create a new, protective canopy. They are the healers. Many, like the alder, have a special relationship with nitrogen-fixing bacteria, allowing them to actively create new fertility in the depleted earth. They live fast, short lives, and in doing so, they create the shade, the shelter, and the rich soil that the slower-growing climax species, like oaks and maples, will eventually need to take their place, a necessary, selfless, and foundational act of renewal. The apical bud of a tree, which is the single, primary growing tip at the very top of its trunk, is a powerful, hormonal commander-in-chief, responsible for the tree's classic, conical Christmas tree shape. This dominant bud produces a constant flow of the hormone auxin, which it sends down the trunk. This downward flowing auxin acts as a powerful suppressant, inhibiting the growth of the lateral or side buds that are closest to it. This apical dominance is why the branches near the top of a pine or spruce are short and small. As the hormone flows further down the trunk, its concentration weakens, which allows the lower branches, now free from its strongest influence, to grow longer and more robust. This simple, elegant, hormonal hierarchy ensures that the tree prioritizes its upward growth, focusing all its energy on its leader, shoot in the critical race to outcompete its neighbors and reach the life-giving sunlight first. The remarkable, invisible senses of a plant allow it to perfectly orient itself in space through a process called gravitropism, the innate ability to perceive and grow in response to gravity. This vital sense is what commands a seedling, no matter how it lands in the dark, chaotic soil, to send its shoot upward into the air and its root downward into the earth. The roots exhibit positive gravitropism, a desire to grow with the pull of gravity. They achieve this using tiny, dense, starch-filled structures within their root tip cells, called statoliths, which are like microscopic pebbles. These tiny weights settle at the lowest point of the cell, signaling to the root which way is down and directing its growth. The shoots, conversely, exhibit negative gravitropism, a command to grow away from gravity's pull, using a similar hormonal sensing system to guide them upward toward the promise of light, a perfect internal biological compass that gives the plant its fundamental bearings in the world. While the subterranean network of fungi can connect different tree species, a more intimate and powerful connection can occur when the roots of two trees of the same species physically graft together, fusing into a single shared circulatory system. This natural root grafting is a common, hidden occurrence in dense, single-species stands, like pine or beech forests. When a root encounters another root from a kin tree, it can recognize it as self and merge its vascular tissues, uniting its xylem and phloem. This creates a deeply interconnected community where resources are pooled and shared, and the forest begins to act as one single large organism. Through these shared pipelines, a healthy sun-drenched tree can shunt water and sugars to a smaller, shaded neighbor, keeping it alive. Most profoundly, it allows stumps of long-felled trees to be kept alive for decades, nourished by the surrounding living trees, a silent, underground network of communal support and shared memory. The stomata of a leaf are the tree's microscopic living mouths, tiny adjustable pores, thousands per square inch, that allow the tree to breathe in the carbon dioxide it needs for photosynthesis. Each stoma is a marvel of cellular engineering, a tiny opening flanked by two specialized guard cells that act like a pair of lips. When conditions are good, with ample water and sunlight, these guard cells inflate with water, swelling and bowing outward to open the pore, allowing the tree to inhale its food from the air. But this breathing comes at a great cost, as water vapor from the tree's moist interior escapes through these same openings. So when the air becomes too hot or dry, or the roots cannot find enough water, the guard cells will lose their turgor, deflating and closing the pore shut, a vital protective act of conservation. The tree must therefore spend its entire life in a state of constant, delicate balance, a silent negotiation between its need to eat and its need to conserve water. The lianas that drape themselves through tropical forest canopies are not trees, but they are a testament to the tree's role as a fundamental living architecture. Lianas are woody, climbing vines that are masters of efficiency, evolutionary minimalists that have foregone the immense energetic cost of building their own strong, supportive trunks. They begin their lives on the dark forest floor, but their sole ambition is to reach the light. They use the trunks of established trees as a ladder, a scaffold, ascending upward, often using hooks, tendrils, or a twisting, snake-like motion to gain purchase. Once in the sun-drenched canopy, they will spread their own leaves, often covering the crown of their host tree and competing with it for light. Their stems, which hang like great woody ropes, are marvels of hydraulic engineering, capable of transporting water hundreds of feet upward with a vascular system that is far more efficient than that of the tree they are climbing. A clever and ruthless strategy of borrowing another's strength to win the race to the sun. The pneumatophores of swamp-dwelling trees, like the bald cypress and the mangrove, are a breathtaking solution to a deadly problem. Living in soil that has no air, tree roots, just like animals, must breathe. They require oxygen to survive and to power the absorption of water and nutrients. In the dense, waterlogged, oxygen-starved mud of a swamp or estuary, this is impossible. To solve this, these trees have evolved snorkel roots, specialized woody growths that grow upward, defying gravity to break the surface of the water and protrude into the open air. These breathing knees, or aerial roots, are covered in a spongy, porous tissue called parenchyma, which allows them to absorb oxygen from the atmosphere and transport it down to the submerged, suffocating root system below, a remarkable, life-sustaining, architectural adaptation that allows them to stand, serene and alive, with their feet planted in two worlds at once. The timberline, or tree line, is the stark, visible, and often beautiful ecological boundary on a mountain or in the high latitudes, the precise elevation or latitude beyond which trees can no longer grow. This line is not an arbitrary one. It is a harsh physiological limit, a thermal barrier dictated by the cold. Trees can only grow where the average temperature during the warmest month of the growing season is above a critical threshold, approximately 10 degrees Celsius or 50 degrees Fahrenheit. Below this temperature, the growing season is simply too short and too cold for a tree to be able to photosynthesize enough energy to survive the long frozen winter. let alone to produce new wood and leaves. As you approach this line, the trees become krummholz, their forms twisted, stunted, and shrub-like, until finally they surrender entirely, giving way to the low-lying hardy grasses and lichens of the alpine tundra, a perfect, visible border drawn by the invisible hand of temperature. On a mountain in Sweden, there stands a modest, unassuming Norway spruce known as Old Chico, which is a living portal to the end of the last ice age. While the visible trunk of this tree is only a few hundred years old, genetic testing of the root system beneath it revealed a staggering truth. This tree has been cloning itself, regenerating from the same ancient rootstock for over 9,550 years. This process, known as vegetative cloning, means that as one trunk has died from the harsh alpine conditions, the ancient root system, safe beneath the soil, has sent up a new genetically identical shoot, again and again, in a cycle of persistence that defies our sense of a single lifetime. This quiet, tenacious spruce first took root when the great ice sheets were just retreating from Scandinavia, its lineage a single, unbroken, living thread, connecting our modern world directly back to the dawn of the Holocene. A profound, 9-millennium testament to the patient, enduring, and quiet life force held within the earth. And so, our journey through the living, whispering world of trees comes to a gentle close. We have walked together beneath their silent canopies, listening to the gentle voice of the wind as it finds its way through their leaves, and we have stood in awe of their sheer, patient scale. We have journeyed deep into the earth, to the dark, quiet realm of the woodbine web, where ancient mother trees share their strength with the young, and where roots gently navigate the soil, sensing their kin and their path. We found the sleeping heartwood, the strong, still center of the tree, and the delicate, living cambium, the ring of endless creation, all hidden beneath the protective armor of the bark. We have seen them as masters of survival, from the snorkel roots of the cypress breathing in the swamp to the gnarled, wind-carved forms of the krummholz at the edge of the world. We have seen them build fortresses of resin, of poison, and of fire-resistant shields, and we have seen them offer profound gifts of medicine, of food, and of cooling shade. From the 9,000-year-old patience of a single spruce to the ephemeral, fleeting beauty of the cherry blossom, they are the planet's great storytellers, the anchors of time, and the very breath of the world, asking only that we rest for a moment in their presence. If you happen to still be awake, that's perfectly all right. You can simply lie back, let the music keep flowing in the background, and drift in and out of the story at your own pace. But if your eyes are heavy, let the stories of trees and the gentle music carry you softly into rest. Sleep well. Good night.